So as we are in the last part of the chapter, chemical kinetics, we are discussing about the numericals based on this chapter, and we'll go based on the numericals and the problems based on the formula which already we have derived in the third session. Okay, that is rate constant of a first order reaction and rate constant of a zero order reaction, half-life of first order and half-life of a zero order reaction. Based on that, I will discuss few numericals today, and then later we will go for the formulas to find the rate constant of first order and half-life of first order, and the unit of rate constant we'll discuss in detail. So today we have two formulas here. One is T half is equal to 0.693 by K, where K is a rate constant, T half is a half-life period. And this formula I'm going to use very well to discuss the numericals today. And K is equal to 2.303 by T log R naught by R, where R naught is the initial concentration, R is a concentration where you stop the reaction. We can find at that particular point what is the rate constant. So first problem I'll take on the order of the reaction. So for a reaction A plus B giving a product, the rate law expression is given by rate is equal to K, molar concentration of A to the power half, molar concentration of B to the power 2. What is the order of the reaction? So if we go back to our basics, they say, what is the order? Order is adding the powers in a rate expression. So to add the powers in a rate expression, they themselves have given the rate expression. You need only to add the powers. That is, rate is equal to K, molar concentration of A to the power half, B to the power 2. Then what is the order? That add the powers. The powers are 1 plus 1 by 2, that is 2.5. We have told you already, the order can be a whole number, it also can be a fraction. So here it is 2, it becomes 3 by 2 and becomes 2.5 for our calculation. So coming to the next part, okay. So coming to the next part, what we discuss here, calculate the half-life of a first order reaction from the rate constant given below. So the rate constant is given. And you know the unit of the rate constant of first order is per minute, per second, per hour, per year. So they themselves have given the value of K using this formula, where T half is equal to 0.693 by K. Using that formula, we can try to calculate the half-life. Therefore, they are given the rate constant as 200 per second. 200 per second. Now I can calculate the half-life. The half-life formula, T half is equal to 0.693 by K, and K value is 200 per second, and if I calculate, I get the value 0.0034. To keep it a standard value, I can write here 3.46 10 to the power of minus 3 seconds. The per second becomes second. So time expressed in seconds because the rate constant is given in per second. The next one, 2 per minute. Again, first order, we can express in per minute also. Therefore, T half is equal to 0.693 by 2. That is 0.346 per minute, or you can write 3.46 10 to the power of minus 1 per minute. The next problem, they are given in 4 years. I told you it can also be given in year, that is per year, they are given 4 per year. So again, if it is per year, T half is equal to 0.6934 per year, then it becomes 0.173 here it becomes. So we have to keep in a standard value, therefore it becomes 1.73 in 10 to the power of minus 1 per year. So this is a 2-mark numerical which comes in your board exam. Of course, the application formula is also utilized for CET and NEET questions also. So knowing the rate constant, I can also find the half-life. Now coming into another type of reaction, giving a T half, we can also find the rate constant. How to go about that? Half-life period of a first order reaction is 20 minutes. They are given T half, they are given is 20 minutes. Now what is or calculate the rate constant? We know the formula here, we can rearrange it. T half is equal to 0.693 by K. Now T half is given, find out the value of K. So K is equal to 0.693 by T half, 0.693 by 20. Therefore the value becomes 0.3465 per minute. Per minute means it is a first order reaction, rate constant of a first order reaction, the unit is per minute. So they are given the half-life, we have found the K. Now coming to the fourth problem, half-life period of first order reaction is 23 minutes. 23 minutes, I need to find the value of K. So calculate the rate constant of the reaction. So K is equal to 0.693 by T half. T half is 23 minutes. Calculate the value, calculate the rate constant K. So we know the formula K is equal to, if K is equal to 0.693 by T half. That is 0.693 by 23 minutes. The value becomes 0.03010 per minute. Again, we could easily find the rate constant provided the half-life is given, or if they give rate constant, we can also find the half-life period. We have utilized the first formula, that is T half is equal to 0.693 by K. We have tried to find both the variables, that half-life as well as the rate constant. So coming to the next type of problems in this chapter, we can also find the rate and rate constant using the formula rate is equal to rate constant into the molar concentration of the reactant. That is, rate is equal to K molar concentration of A. Using this, I can find two parameters. One, I can find rate constant. I can also find the rate. Let me go for the problem number 5. That is, the rate constant of first order reaction is 6.78 into 10 to the power of -2 per second. When the concentration is 0.25 mole per liter, 0.25 mole per liter, calculate the rate of the reaction. So the formula is same formula I can adopt here. Rate is equal to rate constant to molar concentration of A. Rate, that is the rate constant, is 6.78 10 to the power of -2 per second. So I have written here 6.78 10 to the power of -2 into the concentration of A is 0.25 mole per liter. Now, what is the rate is equal to 0. Now I multiply 6.78 into 0.25. I get the value 0.01695 into 10 to the power of -2 mole per liter per second. The rate is always expressed in mole per liter per second. So if I know the rate constant and the molar concentration, I can find the rate. Now moving a little more further, we can take another way of finding the rate constant using the same formula. So rate of a reaction when the concentration is 0.5 mole per liter, 0.5 mole per liter is 5.89 into 10 to the power of -3 mole per liter per second. Calculate the rate constant of the reaction. So rate is equal to K into molar concentration of A. Now rearrange the formula. K is equal to rate by molar concentration of A. Rate 5.89 and 10 to the power of -3. Molar concentration 0.5. The value becomes 11.78 10 to the power of -2 per second. So rate constant expression is always per second. It is a first order reaction. Now moving towards the next type of the problem, that is to find the rate constant of a first order reaction, that is K is equal to 2.303 by T log R naught by R. R naught is always 100. R is the percentage remaining after completion, or if they themselves give the 10% is completed, that means 100 minus 10, 90 remaining. So you will find the rate constant for the 10% completion. Let me try to explain a problem here. 10% of first order reaction is completed in 25 minutes. Calculate the rate constant of the reaction. Therefore K is equal to 2.03 by T log R naught by R. I told you R naught is 100, time they are given 25 minutes. So you can retain in minutes only. Therefore 2.03 by 25 into log 100 by 90. Therefore log A by log B is log A minus B. When I divide 2.03 by 25, I get the value 0.09212 into log 100 minus log 90. You know log 100 is always 2. If you see the log book 10-0, you will get 0.000. Similarly, you take log 90. 90 means 2 minus 1 is 1. 1 minus log 90 0. That is 9542. That means when I subtract both of them, that is 2.0000 minus 1.9542, I get the value 0.0458. That means 0.0912 into 0.0458 multiplied multiply 0.004219 per minute. This is how we can find the rate constant of a 10% completion of a reaction by the reaction which took 25 minutes to complete. That means 90% is remaining, 10% is completed. So we can find the rate constant for the 10% completion using the formula K is equal to 2.303 by T log R naught by R. So as I'm moving towards the next type of problems, a little more further, one derivation is there, or one important conclusion we should come with a problem here. So before that, one more problem I'll try to complete. Eighth one, that is 25% of first order reaction. 25% of first order reaction is completed in 40 minutes. Calculate the rate constant of the reaction. So we know the formula. K is equal to 2.303 by T log R naught by R. For this formula, 2.03 by 40 log 100 by 75. So I can log 100 minus 75. So 2.303 by 40 into 2.00, 100 and 75 is 1.8751. So if I could subtract and multiply with the division of 2.303 by 40, I get the value 0.00719 per minute, because time is given in minutes. So the unit becomes per minute. The unit becomes per minute. So this is how we find the rate constant. Now in relation we need to come to a conclusion, that is show that the time taken for a first order reaction to be 99% complete is twice the time taken to be 90% complete. So let us consider, we know the formula, the K is equal to 2.03 by T log R naught by R, this formula we know. Now let us consider time T as T1, R naught is 100, R is 100, we will take 99% complete, that is 1% remaining, that is 100 minus 99 is equal to 1. Let me come to the basic formula. Let us consider for 99% complete time as T1. 2.03 K log 100 by 1. You know log 100 is 2. Log 100 is 2.00, therefore you will consider it as 2. So T1 is equal to 2.303 by K into 2. Call this as equation 1, or we can call it as T1. Let us consider for 90% completion. So 90% completion, let us consider or call T as T2. R naught is always 100, R is 100 minus 90, 10. Therefore, T2 is equal to 2.303 by K log 100 by 10, that is log 10. Log 10 is 1. Therefore, T2 is equal to 2.303 by K into 1. So, that is T2. Let us divide T1 by T2. T1 by T2. T1 is 2.303 by K into 2. T2 is 2.03 by K into 1. Now we cross multiply. So T1 into 1, T2 into 2. Now we are coming to conclusion. What is that? The time taken for 99% complete is twice time taken for the 90% completes here. That's our conclusion. So that the time taken for the first order reaction, 99% complete is twice the time taken for 90% complete. Therefore, T1 is twice T2. T1 is twice T2. This is the important formula which is there in your textbook also. An important conclusion should come across using the formula of rate constant of a first order reaction. So we are going for the another two different types of problem on the rate constant before I go for the last type of the problem. A first order reaction takes 40 minutes. For 30% decomposition, calculate T half. So to find T half, first I must know the value of K. What they have given is a first order reaction takes 40 minutes, 30% completion. Therefore, we know the formula. So K is equal to 2.303 by 40. 40 minutes, 40 log 100 by 70. K is equal to 2.303 by 40 into, if you take log 100 minus log 70, same what I did for previous one, if you practice it, you will get the value 0.1549. Further, divide this two factor, multiply into 0.1549, you will get the value 8.918 10 to the power of minus 3 per minute. You will get a value 0.008. So standardize the value and retain the value in a standard form, that is 8.918 10 to the power of minus 3 per minute. Now I can find T half. That's what I'm trying to find here. Calculate T half. So T half is equal to 0.693 by K, that is 0.693 by what value I got for the rate constant? 8.918 10 to the power of minus 3. The time T half is 77.7 minutes. So another type of problem, only not finding the rate constant, you can further extend the problem where you can also find the half-life called T half. Now we are coming for a problem here, that is they can also give in grams. Initially 5 gram, after 3 gram, what is the rate constant? So I am trying to explain based on gram. What we discussed was here a percentage, and we could find after KT half. Now let us try to do another problem. The parameter is 5 gram and 3 grams. Let me try to explain the problem based on grams. Let me read the question. Question number 11. A first order reaction has a rate constant of 1.15 into 10 to the power of minus 3 per second. How long will 5 gram? How long will a 5 gram? That means I should find T. How long will a 5 gram of this reaction take to reduce to 3 gram? That is T is equal to, so the formula what we know already, I have rearranged, I took the T to the numerator T and cross multiplied K to the bottom there to the denominator. So T is equal to 2.03 by K, 1.15 10 to the power of minus 3 per second log 5 by log 3, that is log 5 by 3. I can extend the problem 2.303 by 1.15 10 to the power of minus 3, that is per second. At the end of the problem I will tell you how to retain the unit. Log 5 minus log 3. So if you take the same method, log 5 0.50, log 3 0.30 in the log book, if you can see there. Finally you come to a formula T is equal to 2.03 by 1.15 10 to the power of minus 3 into, subtract this 2 of log 5 and log 3 value, you will get a value 0.2219. Then divide this and multiply with 0.2219, you will get time is 444. The unit is per second and the time should be in seconds. So to see that you retain the unit at the end of the problem, time in seconds and K in per second or per minute. So the retaining the unit also is very, very important. These two are the two different types of problems of finding the rate constant T off, then finding the rate time with grams initially, and finally the grams have decomposed. So to find this different problems, problem number 10 and 11 we could explain to you. The last type, of course, the conversion of molecule X to Y follows a second order kinetics, follows a second order kinetics. Okay, this is very important for us, follow second order kinetics, very, very important. Now listen to me here. If the concentration of X is increased by 3 times, so I am increasing the concentration. You know, there are 4 factors which affect the rate of a reaction: concentration, catalyst, temperature and pressure. It may increase or decrease depending on the concentration. So what they are giving us the idea is, if the concentration of X is increased by 3 times, how will it affect the rate of formation of Y? That is, rate is equal to K X to the power 2, because it follows second order kinetics. 2 is here. That's the main equation. Now I'll add, if the X is 3 times increased, the concentration of X is increased to 3 times, how it will affect? Now I'll apply that. Rate is equal to K 3x square. 3 square is 9. The rate is equal to 9 K X to the power 2. That is, the molar concentration of X is second order kinetics. Therefore, how does it affect? What has happened now? I told you, if a concentration is increased, the rate of reaction also increases. That means the rate of reaction will increase by 9 times. The rate of reaction will increase by 9 times because you have increased the concentration of the reactant. Let me come to a same type, another problem. A reaction is second order with respect to a reactant. That is again the same way, it follows second order kinetics. How is the rate reaction affected with the concentration of a reaction? Is 2 types we have. Reactant is either you double it or reduce to half. What happens if you double it? Let me take first the basic rate is equal to K A to the power 2y, because it is second order. So it is a second order 2 here. Now what they say, they say A is doubled. That is, doubled means A is equal to 2A. A is equal to 2A. Twice we have increased the concentration. Therefore, rate is equal to 2 square is 4Ka square. That is Now when I compare equation 1 and 2, I come to a conclusion, yes, when the concentration is doubled, the rate of reaction increases by 4 times. See, the rate is increased by 4 times. Okay, sir, if we increase, then the rate will increase. What happens if we reduce the concentration? We'll take up another one, reduce to half. If the reactant is reduced to half, rate is equal to Ka square, that is 8 to the power of 2. A is 1 by 2, half of the initial concentration, half of the concentration of the reactant A, then rate is equal to K 1 by 2 A square, 1 by 2 square is 1 by 4, rate is equal to 1 by 4 K A, the major equation 8 to the power of 2. Now we know that the rate of the reaction decreases by 1 by 4, that is 4 times the rate of reaction has increased. So when what we discussed in the theory part, and we could also solve that by the numerical, that when the rate increases, it also affects the formation of the reactant. If the rate of the concentration of the reactant decreases, it also affects the formation, or it also affects the rate of a reaction. So we are very clear that concentration plays a very vital important role in deciding the rate of a reaction. I show that by using the rate law, how much a rate of reaction, that is 2NO, nitrogen monoxide with oxygen gives nitrogen dioxide to NO2, will change if the volume of the reaction vessel is reduced to 1/3 of its value. If the rate expression is rate is equal to K NO to the second order 2, that is O2 to the power 1. Now remember, when the volume of the vessel decreases, when the volume decreases, concentration increases. So we'll come to that point later. When the volume is reduced to 1/3 of its value, the concentration of each reactant is increased by 3 times. Remember, when the volume decreases, the concentration increases. Therefore, let me substitute that in the equation. Rate is equal to K NO to the power 2, molar concentration of nitric oxide, molar concentration of oxygen. Rate is equal to K, molar concentration 3 square, 3 square, 9 3 is 27. Therefore, rate is 27 K. We are coming to a conclusion. What is that? When the volume decreases, concentration increases. When concentration increases, it affects the rate. Therefore, the rate is increased by 27 times. So, what is the logic here? How can I increase the rate? Decrease the volume. What happens if you decrease the volume? The concentration increases. If the concentration increases, it will definitely affect the rate of formation, that is the rate of the reaction. The last problem, of course, different method, we'll try to find it out. The rate equation of the reaction nitrogen monoxide with ozone is rate is equal to KNO into O3, the molar concentration of nitric oxide, that is nitrogen monoxide, into the molar concentration of ozone. If the rate is 6.60 in 10 to the power of minus 5 mole per liter per second, when the concentration of nitric oxide, that is nitrogen monoxide, is 1.00 10 to the power of minus 6 mole per liter, ozone 3.00 10 to the power of minus 6 mole per liter, K is equal to rate by NO and into O3, the concentration of nitric oxide, nitrogen monoxide into ozone. So 6.60 10 to the power of minus 5 mole per liter per second, 1.00 10 to the power of minus 6 mole per liter per second, multiply into 3.00, that is, we come across that is 3.00 10 to the power of minus 6 mole per liter. Your mathematical expression, you try to simplify it. As you simplify, you get an answer. The answer is 2.20 10 to the power of 7 per mole, molarity. Because mole per liter gets cancelled, you will get per mole liter per second. That's why written capital M per second, that is per molar per second, or we can write the expression per mole liter per second. So this is how we could try to solve. I would try to cover all the different types of problem on this chapter, but all we discuss in theory, we have come to the conclusion. So half-life, first order, then concentration increases, concentration decreases. Find T half by finding K. Find K by grams also, that is 5 gram and 2 gram, not always in the percentage. If they give the rate expression, find the order. So I expect you all to work the numerical which is there, which is there displayed and which I have worked out, which I explain in detail. So try to work Definitely it'll be interesting, provided you take a pen and paper. Along with that, use a logbook to know the values. It'll be interesting. So by this, I have completed all the numericals, all the numericals of different type in the chapter chemical kinetics. Thank you so much. God bless you all. Thank you.